Good morning, everybody. Welcome to the lecture for March 23rd. Just a quick announcement before we begin. I made this announcement on Canvas as well, but this week for the Wednesday problem sessions, they don't necessarily need to be on Wednesday. I'm just asking you to please form your own groups of 3 to 4 people. If you're don't have anyone's contact info in class, you can use the discussion board I posted. Just post what days you're free, what times you're free, and try to, or join an existing group. The groups need to be at least 3 people, and at most, we'll say 9 again. 9 was the max I set last time. And to get credit this week, you really need to participate at least once by asking a question, answering a question, or just sort of being involved. More than raising your hand, you need to actually say something with the voice chat or the text chat. Okay, so today we're continuing section 1.6. Last time we ended with Fermat's theorem, which told us about the order of elements in prime moduli. So if you have a prime modulus, we learned that the order of a multiplicative element, of an invertible element, always divides p minus 1, where p is the prime number that's your modulus. And so the rest of section 6 is devoted to proving this more generally, if you have not necessarily a prime modulus, but a general modulus. And the answer will depend on this new function we're going to introduce right now, which is Euler's phi function. So what does it do? Well, Euler's phi function just counts the number of things smaller than n, so at most n minus 1 and at least 1, that are coprime with n, which is exactly the number of things that are invertible in this set Zn, right? And Zn denotes a set of equivalence classes, so this is a set of sets. There's n minus 1 elements, n elements. We don't include the 0 class because 0 is definitely not invertible. But the rest of these could be invertible. So we just count which of them are invertible, and we throw out the 0 divisors. So this number will be very important. And so the first few theorems today we prove will be about counting this number. So let's get started. What's our first theorem? Our first theorem says that if p itself is prime, and you take any natural number, then phi of that power of p is p to the n minus p to the n minus 1. Now this is we've already proven this for n equals 1, right? If n equals 1, then this is p minus 1. And that's just saying that every element here is invertible. We know that in prime moduli everything is invertible because everything is coprime with the modulus. This theorem isn't much more difficult to prove. Basically, we use the unique prime factorization theorem. So notice that the GCD of a and p to the n is always p to the k. P to the k is the largest power of k dividing a by the unique prime factorization theorem. Okay, that means that the only things that have GCD equal to 1 are things that p itself doesn't divide. Or the only things the only elements which are zero divisors are p, all the multiples of p. So I list out all of these multiples, and I go all the way up to p to the n. So how many multiples are there? Well, this is p to the n minus 1 times p. So there are p to the n minus 1 elements in this list. So I subtract that from all the elements from 1 up to p to the n, and I get exactly this. Every other element is invertible. Phi of p to the n is the total number of elements in the total number of congruence classes minus the number of congruent classes that are zero divisors. And here I include 0 itself as a zero divisor, which is represented by this class here. Right, p to the n is congruent to 0 mod p to the n. So I subtract that as well. So this is a nice little theorem. Right, we checked last time that phi of 8, which is 2 to the third, is 8 minus 4, so it's 4. And it's all the odd numbers, right? 1, 3, 5, 7. This was in your last homework to check which elements are invertible. Okay, so this is theorem 1.6.5. Our next theorem also has to do with counting or computing phi. And the last theorem combined with this theorem gives us a very efficient way of computing what phi of any number is. You can always just write out all of the numbers, but this will give us a very efficient way so that we don't have to do that and check manually which ones are coprime. So what's this theorem? This theorem is theorem 1.6.6. So here we're going to take two coprime numbers. So this is sort of the opposite of prime powers. So prime power is obviously p times p. P in itself, p to the l and p to the k are never coprime. So if I take two coprime numbers, then the Euler function of a times b, their product, you just multiply the Euler functions of a and b. And the proof actually uses a lot of ideas from chapter 2. So let's see how those come up. So how are we going to do this? So let G sub A be G sub A and G sub B denote the set of invertible elements of ZAB, ZA, and ZB, respectively. So G sub AB is a set of invertible elements in ZAB, GA is a set of invertible elements in ZA, and so on and so forth. So we will find a bijection let's give this bijection a name, F, from G sub A cross G sub B to G sub AB. right? And this is enough. I know that the cardinality of this, if there exists such a bijection, by what we proved in chapter 2, the cardinality of this set is equal to the cardinality of this set. And the cardinality of this set is the product of the cardinalities of A and the cardinalities of B. Remember that this is the set of ordered pairs. So let's define this bijection and then prove its bijection. So let x belong, let the pair xy belong to GA cross GB. So by the Chinese remainder theorem, this is one of the theorems we proved recently, I can find an element which is unique modulo AB. So it represents something in, well, actually I don't know it's in GAB yet. I only know it's in ZAB, such that Z is congruent to X mod A, and Z is congruent to Y mod B. So the Chinese remainder theorem tells me that if I pick two numbers, one modulo A and one modulo B, and A and B are co-prime, this is very important as part of the assumptions of the Chinese remainder theorem, then I can set the modulus, I can solve this modulo equation simultaneously. I can find an element, an integer Z, such that Z is equivalent to X mod A and Z is equivalent to Y mod B. And we also proved that that integer was unique up to Z AB, right? It's unique modulo B. Unique modulo AB. Okay, and this is our image. So define f of z. F of x. F of xy to be equal to z. So what do I need to prove? To finish the proof, I need to prove that this function is injective and surjective. So notice that to see injectivity, it's just even more basic. Suppose f of xy, x1, y1 is equal to f of x2, y2. And this was z. So then x1 is congruent to z, right, by our construction, but it's also z is also congruent to x2 mod A. So x1 and x2 represent the same congruence class. And similarly for y1 and y2. Z is chosen to be congruent to y1, and also because z was produced from this pair of numbers, it's also congruent to y2. This means that x1 is congruent to x2 and y1 is congruent to y2. So the pair xy represents the same pair in this product. Okay, sorry about that. So the difficult part is surjectivity. So suppose that Z is an element of GAB. Well then, Z the GCD of Z and AB is equal to 1. But by the prime factorization theorem, that means that all of the primes that appear in Z don't appear in either A or B. Which means that, in short, the GCD of Z and A is also true, is also 1. So now what do I want to do? I want to divide Z by A to get the residue modulo A. So Z is going to be equal to K times A plus R. And actually, let's call it X, suggestively. Because what's going to happen? Z is congruent to X mod A. And since the GCD of Z and A is 1, the GCD of X and A is also 1, because all I've done is add a multiple of A. Then I can do the same thing to find a Y. But instead I divide it by B. L times B plus Y. And Y is also going to have GCD of Y and B is equal to 1. So f of xy is exactly equal to Z. Right? Z is the element which is congruent to X mod A by construction, and Y mod B. And what does surjectivity ask for? It says surjectivity means that whenever you give me an element of the codomain, which is in this case GAB, so that's what I chose Z to be, I need to find a pair X and Y such that f of xy equals Z. So this proves that f is surjective. So because it's both surjective and injective, it's bijective, and I get that the cardinality of these two sets is the same, which is to say that phi of AB is phi of A times phi of B. Okay, so let's see this proof in action and check that it actually works. And also see how to apply the last two theorems, in fact. So let's try this exercise. Compute phi of 12. Well, the thing to do here is to write 12 using its prime factorization. So it's 2 squared times 3. Yes, 2 prime factors. Phi of 2 squared by the first theorem is 2 squared minus 2, which is just 2. And phi of 3 is just 3 minus 1, so it's also 2. So phi of 12 should be the product of these two things, right? Because 2 squared and 3 are coprime. So this is going to be 2 times 2, which is 4. So I expect to find 4 elements which are coprime to 12. And let's check. if I list out the congruence classes, I have 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11. So which ones are coprime with 12? This one is invertible. This one's not because it in fact divides 12. This one is not. 3 divides 12. This one is not. This one is. This one is not. This one is. This one is not. This one is. This one is also not. Oops, this one is not. Coprime. Not coprime, not coprime. Coprime. Right, this is not coprime because 2 divides both 10 and 12. So there are indeed 4 elements. And how did our proof go? Our proof said, okay, let's look at Z4. When I got this product rule, and in fact, we want to look at G4, which is the set of all elements invertible modulo 4, which is just 1 and 3. And I also want to look at G3, which is a set of invertible elements modulo 3. And I want to find something that's congruent to 1 in both 3 and 4. So it's got to be 1 more than 3, a multiple of 3, and 1 more than a multiple of 4. And it should be one of these elements. Let's check which one it is. And that's exactly going to be 1. Right? 1 is 0 plus 1, 0 plus 1. Let's try to find this element. I need to find something that's 2 more than a multiple of 3 and 1 more than a multiple of 4. Well, that's going to be this one, right? 5 is 1 more than a multiple of 4. It's 4 plus 1, and it's 3 plus 2. Right, so in this table, I'm filling in the elements of Z12, and this is the elements of G3. These are the elements of G4. For this one, I need it to be 3 more than a multiple of 4 and 1 more than a multiple of 3. That's going to be 7. This is 3 more than a multiple of 4 because it's 4 plus 3. And it's only 1 more than a multiple of 3 because it's 6 plus 1. Which means that the last one has to be 11. And let's just check. 11 is indeed 3 mod 4. It's 8 plus 3. And 2 mod 3. It's 9 plus 2. So this is a justification that the formula's worked, and it shows what's hidden behind this formula. It's exactly this Chinese remainder theorem. Now, the whole point of the formula is not to be able to do this. It's to be able to do it for extremely large numbers that you would have a hard time doing it for anyway. So let's do another example where we have a large number involved. Let's compute phi of 96. Well, I could write it all out, and it would be some huge list, and I would cross out all the 0 divisors. Or I could write 96 as 32 times 3. 32 is 2 to the 5th times 3. By the last theorem, since 2 to the 5th and 3 are coprime, I get this. And then I use my prime powers formula. So this is 32 minus 16 times 3 minus 1. So it's 16 times 2, or 32. So there are 32 numbers coprime with 96 that are less than 96. Okay. So there's one more theorem I'd like to prove today. So far we've only found how to compute phi. We haven't seen the way in which it's useful yet, and that's exactly this last theorem for the day. Let's bring this up so you can see the entirety of the statement. So what does the theorem say? It says I choose an arbitrary n, which is my modulus, and I'm going to let the GCD of a and n be equal to 1. So a is an invertible element in n. So what did we say? If n was prime, we already knew this theorem. This was called Fermat's theorem. But now I have to do a little more work. The order of a in Zn doesn't necessarily divide n minus 1. It divides this Euler phi function, which happens to be equal to n minus 1 if n is prime. So this is a natural generalization of what we proved before for an arbitrary modulus not necessarily prime. So let's write a proof. So the proof is almost the same as it was before. So list all elements of Gn. B1, B2, and by definition, the number of elements in Gn is 5n. The last index I get here is 5n. And Gn was defined to be the set of invertible elements. Well, just like before, when I multiply these elements by a, I get the same thing. So multiplication by a is a bijection. This is just going to be the same set of elements listed in a different order. So because these elements and these elements are the same, and multiplication commutes, and it doesn't matter what order it comes in, when I multiply all the elements here, and I get a number, and then I should get the same number if I multiply all of the elements here. And so I'm multiplying. This is equal to AB1 times AB2 and it's not equal to, it's congruent mod n, right? All these equalities are happening mod n. So this is the same set modulo n. Now I just divide both sides of this equation. I multiply by all of the inverses of each of these one by one. I multiply by the inverse of b1, and I cancel it with the b1 here. And how many a's are there? Well, there's 5n a's. So a to the 5n is congruent to 1. Which means that the order of a actually has to divide 5n, right? Because the loop that you get when you start taking powers of a has to close up when you take the 5nth power. And this is the proof. This proof is actually probably the easiest one just because it's so similar to the proof of Fermat's theorem once you define phi of n. So it's a very nice thing. It shows why phi of n is an interesting function and why we cared so much about computing it. I think that's going to be it for today's lecture. Please let me know if you have any questions. And I will see you for Monday's lecture, or Wednesday's lecture. Have a great day.